Good morning, Zachary. Thanks for joining in. We'll get started here shortly.
Okay, good morning.
All right, thanks for joining in, Zachary. We'll go ahead and get started. Let me share my screen. Okay. And I did put the video from Tuesday's class out for you if in the event you need to review it. So here we are. On Tuesday, I reminded you about the project article that you need to be getting approved by this Saturday. If you need to, refresh yourself on the project article that you're supposed to be finding, is part of Tuesday's video. You can go back and watch that. There's also some other project videos in the announcements that you can take a look at. And if you're looking for information on the project, for now, the easiest way to get to it is just to click on the weekly overviews and look under this link that says project article approval. If you click there, there's a link to the project, okay? And that project article approval deadline has the instructions on how you get your article approved. You have to send me the full article as a PDF attachment so that I can review it if you have not done so already. And when you click on that project link, if you're looking for information, the project details has what you're looking for. But I covered that information on Tuesday again. So feel free to go out and take a look at that. All right, so here we are, the weekly overviews. This week, we started dealing with gravitation. I covered the material in the readings and viewings notes. What I wanted to do today was to go out and solve some sample problems with you dealing with gravitation, okay? And so I'm going back to the announcements, and at the very bottom used to be, this was the last item, but now you can click on this extra resources, and if you click again, here's taking a minute. Sorry about that. All right, so let me minimize this and get it out my view here. Okay, so I'll go through a few of the other screens that I have available here, and then I'll jump in and solve these two example problems that I have, and we'll finish up by looking at the connection between gravitation and uniform circular motion, okay? So I have bookmarked for you here in this document that says gravitation links, several videos and websites that cover some of the topic areas that we discussed on on Tuesday and others. You can go to those websites and you know, do some additional reading if you want to, and watch these additional videos that I've made available to you. This particular screen, again, summarizes the universal law of gravitation. There's the formula. It reminds you of the units that are involved if you're solving for force. We talked about on Tuesday that in order to find the gravitation force, you need to take the mass of the two objects and multiply, and you need to divide by the distance between them squared. I've listed for you the value of the gravitation constant along with its units. And I remind you that I talked about on Tuesday that the gravitational force obeys what we call an inverse square law, because it's proportional to 1 over the distance squared. Okay, so that's just a quick summary of pretty much what we talked about on Tuesday. It's always good to have, you know, to be thinking a bit about these equations when you're using them. And one thing students sometimes get confused is the big G, because it deals with gravity, and little g because it deals with gravity, right? But you have to remember that big G is a constant. It is the same for the entire universe. Okay, it's a very small value, because if you notice the exponent was 10 to the negative 11, but it's still constant throughout the entire universe. But little g, however, is for a particular location in the universe. So it's location specific, and it's not constant. For example, on Earth, the value is 9.8 meters per second squared. But if you go to our nearest neighbor, the moon, it's 1.7 meters per second squared. So big G is a constant, little g is for a particular location. And one of the things we're going to look at today is this idea of weight and how it ties in with gravitation. And you know, when we're dealing with weight, we're dealing with little g. Okay. This slide here, it reminds you what I just said. Be on the lookout for the relationship between weight and the gravitation force. So in the formula, that the way I wrote it, the M1 and M2 are the masses of the objects. You know, on Tuesday we looked at the formula and they had what? Big M and little m. Same thing. Two objects, you need their mass, whether it's big M, little m, M1, M2, or some other notation that they're using to represent mass. You need the mass of the objects in kilograms. And then R is the distance between the two objects measured from their center. Okay. So I'm explaining the variables in the formula here, right? And so as M gets bigger, the gravity force is going to get bigger. And remember, I talked about on Tuesday that you need fairly nice sized objects before the gravitation force is really felt. Because if you have little objects, you can't overcome the smallness of big G, right? As the R gets bigger, the gravitation force gets smaller, right? So objects that are far, far away, even if they're big, the distance might be too much to overcome. And I gave the example on Tuesday of Jupiter. Jupiter is much bigger than the Earth, and yet you don't feel the pull of Jupiter on you because it's so far away. Okay, so that's the 4 items that I have listed there on the bottom. We'll get back to these other 2 pictures. We'll talk about them here shortly, but what I want to do now is solve these 2 example problems for you, or share my solutions to these 2 example problems. Okay, and you will be expected to utilize the gravitation formula, especially on problem set number 8. Problem set number 8 is not until next week, but still you're going to be expected to use that formula. Okay, so it says, determine the force of gravitational attraction between the Earth, and they give you the mass of the Earth. So that's one of your M's, and a 70 kilogram physics student. And there's your other M, right? So you got M1 and M2, you got little m and big M, right? So it says, find that gravitational attraction if the student is standing at sea level, a distance of 6.38 times 10 to the 6 meters from the center of the Earth. Okay, when you measure the gravitational force, the distance between the objects, you measure from center to center. Okay, so they're imagining basically that the person standing on the Earth at sea level is very small compared to the distance from the center of the Earth. So basically that 6.38 times 10 to the 6 meters is the radius of the Earth. Okay. And so what you do with this problem is you substitute the values. There's big G again, there's M1, there's M2, and the distance. See, they use D, right? They're using D, but D and R, the distance, that means the same thing basically, okay? So that's another thing, you know, you have to get comfortable with this idea of different books or use different notation, but if you understand what the variables represent, then it doesn't matter what symbol they use, right? M1, M2, big M, little m, R, D, whatever, however they want to write it. Okay, so now take the formula and substitute in. So you see on the top, you have big G, 6.673 times 10 to the negative 11 Newton meter squared per kilogram squared, okay? And then you have M1, which is the mass of the Earth, 5.98 times 10 to the 24 kilograms. That's the mass of the Earth. And then the 70 kilogram student, okay? And then what you're dividing by on the bottom is the distance squared. So you have to take the 6.38 times 10 to the 6 meters and square it, okay? Now, if you have one of those fancy scientific, you know, calculators, the only thing I'll tell you is you have to be very careful how you group things in the calculator, or it will give you an incorrect answer, okay? So I don't use a calculator, one of those fancy ones at least. So what I have to do is I have to take the numbers and do them alone, okay? So you can see here, right here, equals 6.673, 5.98, and 70. That's the numbers from the top. And then 6.38, that's the number from the bottom, but I squared it, okay? And when I multiply all of that, I get 68.6, okay? Then I have to separate out the exponents, okay? So I do the numbers by themselves, the exponents by themselves, and then I recombine it at the end because, again, I'm not using a fancy calculator, so I have to, you know, I have to work it out the long way, okay? So that in the top, I have 10 to the negative 11. I have positive 10 to the 24, okay? On the bottom, I have 10 to the 6, and I'm squaring it because the number has to get squared and the exponent. And actually, the unit is getting squared too, but we know we're finding force, so we don't have to worry about that because we know everything's going to cancel out, and all you're going to be left with is newtons, right? Okay, so now let's work out the exponent. 10 to the negative 11 times 10 to the positive 24. When you multiply exponents, you add them together. That gives you 10 to the 13. 24 minus 11 is 13. On the bottom, you have 10 to the 6 squared. When you square an exponent, you multiply. When you raise an exponent to a power, you multiply. So that becomes 10 to the 12. 6 times 2 is 12. So now I have 10 to the 13 divided by 10 to the 12. The rules for exponents say when you divide exponents, you subtract. So that becomes 10 to the 13 minus 12, right? So 13 minus 12 is 1. So that's why I have equals 10 to the 1, okay? So the number part of this gives me 68.6, and the exponent is 10 to the 1, which is basically 10, right? And my unit is newtons. So when I multiply that out, 68.6 times 10 is 686 newtons. That's how you get the answer. Okay. Are there any questions about what I did there?
No, ma'am, I'm good.
Okay, because this is the kind of thing you will be expected to do when you're using the gravitation formula, okay? And you'll use the gravitation formula to find force on problem set number 8. You know, you may have an occasion to utilize it to find any variable that's missing, right? In the lab class specifically, you're gonna be using the same formula where they give you everything except big G. And you're gonna be, so you'll have the force, the masses, and the distance, and you're gonna solve for big G. So you have to be comfortable with this idea of doing the exponents and that kind of thing, right? But that's, you know, stuff you covered in a kind of a math class, right? Or you should have, right? Now, what I want to do with this problem before I look at another example is I want to compare what I get for the gravitation force, 68.6 newtons, and what I get for this student's weight. Now you have to go back to Newton's second law, and remember the way you find weight is you take the object's mass times gravity, right? Not big G, little g. So you see on the far left, I've done W equals mg. So I take 70 kilograms times 9.8 meters per second squared. And when I multiply that out, I get 686 newtons. If I multiply 70 times 9.8, I get 68.6, okay? No, sorry, I get 686. I need more coffee, sorry. Okay, so you see, this student is standing at sea level on planet Earth. Planet Earth is the biggest thing pulling on this student. So that's what gives the 70 kilogram student weight. And the weight is 686 newtons, but the force of attraction between the Earth and the 70 kilogram student is also 686 newtons. When an object is standing on a planet, on a moon, you can get the weight by doing m times little g, or you can get the weight by looking at the gravitation force because they're equivalent, right? And that is because this student is standing on planet Earth, okay? That's why we can do m times little g, all right? They're equivalent. But let's look at this other example. So by now you might be thinking, oh, well, I can just, instead of doing all this stuff, I can just do m times little g, right? Why go through all the craziness with this gravitation formula, numbers and exponents and all that? Here's why. It says, determine the force of gravitational attraction between the Earth, there's the mass of the Earth again, and a 70 kilogram physics student if the student is in an airplane at 40,000 feet above the Earth's surface. This would place the student at a distance of 6.39 times 10 to the 6 meters from the Earth center. And you might be thinking, that's not that big of a difference. So why does it matter, right? Well, if you go in and substitute and you do the same math, take out the numbers. So all of the numbers on the top are the same, but on the bottom you have 6.39 and you're squaring. And that'll give you 68.4. You do the exponents, you still get 10 to the 1 because all the exponents are the same. So you get 684 newtons. So you see, the student is now off the planet. They're not on planet Earth. They're not standing at sea level. They're in a plane 40,000 feet above the Earth. And you can see the amount that the Earth pulls on that student is going down. Here's the thing though, you can't do W equals m times little g because they're not on the planet. That's the beauty of the gravitation formula. No matter where you go, as long as you know the mass of the objects and how far apart they are, you can figure out how much gravitational attraction between those two objects. And you can do that for any two objects in the universe. That's pretty powerful stuff to be able to do that for any two objects in the universe, okay? That's what the universal gravitation formula means, okay? So we're not relegated to just figuring out an object's weight. on the surface of a planet or on the surface of a moon or on the surface of an asteroid or whatever, wherever they're at, all we need to do now is figure out how much mass and how far apart, and we can find the gravitational force. Okay, any questions about that?
No, ma'am.
All right,
No,
good. All right, so those, again, in the extra notes folder, extra resources folder, those two examples that I worked are there, okay? The only other thing I want to do is take a look at these two other pictures I have here. And one of them has some writing on it and one of them doesn't. So I'm going to open this one first. And I'll just say to you up front, I don't expect you to do any of this math that I'm showing you here, right? In terms of how we get to that point of these formulas, okay? I don't expect you to derive anything, but using these formulas, yes, okay? So what I want to do now is I want to take our old circular motion stuff. This is the stuff you had on your midterm about the satellite, okay, for example. And I want to compare it to our new gravitation stuff. So I want to use my circular motion stuff to look at orbit motion. And then I'm going to use my gravitation stuff to look at orbit motion, okay? And so there's some things that we need to work out here, okay? The big M represents the mass of a planet, any planet. The little m, okay, M2 represents the mass of our satellite, okay? Little m or M2, okay? R is the orbit radius. So the distance between the center of the planet and the center of the satellite. Okay, how far out is it orbiting from the center, right? V represents the orbit speed. T, big T, is the period. Okay, we're familiar with that orbit speed and orbit radius and period because you had to use that on the satellite problem, right? And then AC, we know that. That's centripetal acceleration, okay? So just kind of setting up some terminology there for you, all right? So when you're comparing circular orbit motion to gravitation orbit motion, the thing you have to recognize is it is the force of gravity that's keeping the satellite in orbit. I mean, if I were to ask you, why does the satellite stay up there? Gravity, right? But up to now, we hadn't really been dealing with the force associated with orbit motion because we're just learning forces, right? And in particular, we're just learning the gravity force. But what you need to understand is the centripetal force, the circular motion force, is equivalent to the gravitation force because gravity keeps the satellite in orbit, okay? So when we equate those two forces, and that's what I'm doing in the red print there, okay? When I equate those two forces and do some algebra, okay, which I would never ask you to do, what you wind up getting is an equivalence between the circular motion of variables properties and the gravitation motion properties, okay? And that happens because gravity is what's keeping it in the circular orbit, okay? So in the box, you see the centripetal force, okay? To get centripetal force, we go back to Newton's second law. Force is equal to what? Mass times acceleration. Centripetal force, F with the little subscript C, is equal to mass times centripetal acceleration. So that first line, that's just Newton's second law. Force equals mass times acceleration. I'm just applying it to centripetal acceleration, okay? But I have to remember from my circular kinematics that the centripetal acceleration is equal to V squared over R. So I get the centripetal force, M V squared over R, okay? All right, now you see the formulas on the far left, V equals 2 pi R over T, AC equals V squared over R. You've already been using those formulas, okay? So that's our old circular motion stuff. The only thing new we looked at is with circular motion, is the centripetal force. And we can do that now because of Newton's second law, force equals mass times acceleration. But what you have to remember is that centripetal force is equal to the gravity force. And that helps us to get the formulas on the far right. So now, to find the speed, we can do 2 pi over r, or we can do square root g big M over r. Either way, they're equal. So our circular motion speed is equal to our gravitational motion speed. So square root big G big M over r. Remember, big M is the mass of the planet, r is the orbit radius. It doesn't matter what planet. Okay, so if I want the speed that this satellite is going to orbit, I have to take square root big G big M over the orbit radius, or I could do 2 pi times the orbit radius over the period. Either one, because remember, gravity is keeping it in orbit, so its speed is a result of the gravitational pull. Okay, what about the centripetal acceleration? To get the centripetal acceleration, I can use my old formulas on the far left, v squared over r, or I could use my new gravitation formula, big G big M over r squared. Okay, so I have 2 ways now to figure out the centripetal acceleration. You've already used the formulas on the left, the circular motion formulas. So in problem set number 8, and then subsequently on the final exam, I will be challenging you to use the gravitation formulas on the right. Okay, now there's one relationship on the far bottom. You see it. The period squared is proportional to the radius cubed. You see it? Big T squared, and then that little squiggly line, proportional to the radius cubed. That is Kepler's law. On Tuesday, I introduced you to 3 of Kepler's laws, and the very last one, Kepler's third law, I told you was what Newton used to help figure out the gravitation formula, the gravitation relationship. Okay, and so that last one, the period squared is proportional to the radius cubed, that comes right out of Kepler's third law. Okay, so now you have the connection between circular orbit motion and gravitation orbit motion. All right, any questions about that?
No, ma'am.
All right, and the last picture is pretty much the same thing without the red writing, because I'm never going to ask you to derive any of that stuff. So the red writing was just like extra, but these are the formulas that you need for circular orbit motion, gravitation orbit motion. Okay, and I didn't write the force for gravitation motion, but that's Newton's universal law of gravitation. Right, if I were going to do the force equals big G M1 M2 over r squared, right? All right, so that's pretty much what I wanted to cover with you today. I wanted to show you some examples, show you the connection between our circular motion and gravitation motion, and then, you know, share some resources that are available to you to help, you know, if you want to have some extra material to review. Okay, what questions do you have of me?
Do we still have lab at?
What on Tuesday? Nobody showed up. Nobody showed up for lab on Tuesday. So yeah, we definitely need to have lab, because I need to explain the experiment to everybody. But you know, I don't make recordings talking to myself. So when folks show up, then I'll cover it.
Yeah, that's fine. I was just double checking to make sure. I was just
All
busy.
right.
Didn't make it on Tuesday, so.
Yeah,
I
yeah.
can just see you like do it
I'm there
review.
today.
Okay, thank you.
All right now. All right, that wraps up today. Thanks for joining in. While you're working this weekend, if you have questions, don't hesitate to reach out to me. So stopping the recording.